Another electrophilic substitution reaction of benzene is Friedel-Crafts reaction. Now Friedel-Crafts reaction is of two types: Friedel-Crafts alkylation reaction and Friedel-Crafts acylation reaction. In Friedel-Crafts alkylation reaction, an alkyl group is entered in benzene ring, and in acylation reaction an acyl group or acetyl group can be entered in benzene ring. So in alkylation, FC, Friedel-Crafts alkylation reaction, let us see what happens. You know, the alkyl group means the methyl, either it can be methyl or ethyl or propyl or tertiary butyl, any of them. So if we want to see this methyl group into the benzene ring, here we take benzene and this group has to be entered into this benzene ring to make this compound benzene, and here CH3, and this compound is known as toluene. This compound is known as toluene. Now how can we make this? We have to take this alkyl group and an halide of this alkyl group. That means halide means you can take CH3Cl or CH3Br or CH3I. Now we take here the CH3Br, and in presence of, you can keep CH3Br, or you can also take CH3Cl, methyl chloride, in presence of anhydrous AlCl3. Okay, if you take this, if you treat benzene with methyl chloride in presence of anhydrous aluminium chloride, then toluene will be formed. The reaction mechanism is very simple. As aluminium chloride, you know that aluminium, electronic configuration of aluminium is, the atomic number of aluminium is 13, that is 1:2, 2:2, 2p6. 1:2, 2:2, 2p6, that means configuration of neon, and after then 1:2, 2:2, 2p6 means 10, and then 3s2 and then 3p1, that is the electronic configuration, that is the outermost shell electronic configuration of aluminium. Okay, here in 3s orbital 2 electrons are present, and in 3p orbitals only 1 electron is present. Now if 1 electron from 3s shifts to 3p orbitals, then the number of unpaired electrons here is 3, 1 in 3s orbital and 2 in 3p orbitals. So aluminum can make 3 bonds with 3 chlorine to form LCl3. Now after formation of this all unpaired electrons get paired, still this pz orbital remains vacant. So in aluminum chloride, the central atom aluminum has a vacant pz orbital. Now if anyone can give a paired electron, that means there are lone paired electron or negative charge to aluminum chloride, aluminum can accept that paired electrons and can accommodate it in its vacant pz orbital. So we can say aluminum chloride is a lone pair acceptor or electron pair acceptor, and you know which can accept lone pair or electron pair is called a Lewis acid. So aluminum chloride is a Lewis acid. Now let's see how the reaction occurs. When you add CH3Cl methyl chloride in benzene, the reaction can occur but in very slow rate. Why the reaction would occur? As chlorine is more electronegative than carbon, the bond pair electrons, it will pull the bond pair electrons, and at the same time the CH3 group, methyl group, you know, methyl group has plus I inductive effect. Plus I inductive effect means the tendency to push the bond pair electrons to the other end. Okay, so these two facts actually make a charge separation in CH3Cl molecule. Here on carbon some partial positive charge will be there, and in chlorine some negative charge will be there. So an electrophilic center has been generated. So pi electrons can attack to this carbon. To actually increase the rate of the reaction, a catalyst is used, which is aluminum chloride. Now this aluminum chloride is a Lewis acid. It can accept the lone pair electron from chlorine. Chlorine has a lone pair electron, so chlorine can make a coordinate bond with this aluminum and aluminum chloride. So when a coordinate bond is formed, chlorine cannot make 2 bonds at a time, so this bond has to be broken. Okay, so chlorine, this bond pair electrons will go away with chlorine, and CH3 group will have a full positive charge. That means a methyl ion CH3 plus ion will be formed, and here along with LCl4 minus, as the bond pair electrons go away with chlorine, so aluminum will have or the excess paired electrons comes in aluminum, so aluminum will have a negative charge. Aluminum LCl4 minus ion will be formed. Now this attack will be very easy. As this CH3 plus ion is formed, the production of this carbocation will make the electrophilic attack. That means pi electrons now will come faster to attack or to make a bond with this carbon of CH3 group. So what will be formed as the bond is broken from this carbon? So here a positive charge will be formed, and CH3 will go above the plane, and hydrogen was already there, which will go below the plane. Now what happens? Hydrogen gives its bond pair electrons and removed as H plus ion. So here H plus ion is removed, and again benzene is formed with CH3 instead of hydrogen, but hydrogen atom is there. Now hydrogen is replaced by CH3 group, now toluene is formed, and this H plus, and here LCl4 minus ion is also formed, H plus, and this Cl minus ion will combine to form HCl, and again LCl3 will remain unchanged. So aluminum chloride just acts as a Lewis acid in the reaction, in the Friedel-Crafts alkylation reaction. Okay, so this is the simple mechanism of Friedel-Crafts alkylation reaction. We need to take CH3Cl or any alkyl group you want to add to the benzene ring, its halide, the halide of that alkyl group, along with anhydrous LCl3, where anhydrous LCl3 acts as a Lewis acid. At the very beginning, what happens? The chlorine, or you can take bromine or iodine, whatever. So this chlorine, which was bonded with CH2 group, that is with the alkyl group, make a coordinate bond with aluminum chloride and get separated to form LCl4 minus ion, and as that is why CH3 plus ion is formed. Here, see, here this carbon was carrying a partial positive charge, but here a whole positive charge is on this carbon. So rate of attack by the pi electrons of benzene that must be faster here than in absence of LCl3. Okay, so that is why we can say aluminum chloride acts as a Lewis acid in Friedel-Crafts alkylation reaction. Now let's consider some other reaction which is also Friedel-Crafts reaction, Friedel-Crafts alkylation reaction. Now in Friedel-Crafts acylation reaction, an acyl or acetyl group is entered into the benzene ring. Acetyl group means this CH3 single bond C double bond O. This group is entered in benzene ring in Friedel-Crafts acylation or Friedel-Crafts acetylation reaction, and the product is benzene with this group bond C double bond O, and here CH3, and this is a ketone, as here a phenyl group, and on the other end of this carbon a CH2 group is present, and between a carbonyl carbon is present. So this is a ketone group and its name is acetophenone. And if two phenyl group is on the two sides of this carbonyl carbon, then it is named as benzophenone, and if two CH2 groups are there, this is acetone, you know. Now how can we make this? Just like the Friedel-Crafts acylation, just like the Friedel-Crafts alkylation reaction, we need to take the halide of this acetyl groups. In the alkylation of benzene, we take the halide of the alkyl, that particular alkyl which we want to get into benzene ring. So here, if we want to enter CH3CO group in benzene ring, we need to take CH3CO Cl, maybe beer, maybe iodide. Okay, so you have to take the acetyl halide along with anhydrous LCl3. Again, anhydrous LCl3 will act as a Lewis acid, and the reaction mechanism will be almost same. So here benzene, and if we take CH3COCl, CH3COCl, this is an electrophilic center, as chlorine is more electronegative than carbon, and this oxygen is more electronegative than carbon, and the pi electrons are shifted more towards the oxygen atom, making it partially positively charged, and this oxygen partially negatively charged. So benzene may attack to this carbon, but to make the reaction faster, we add LCl3, where the chlorine make a coordinate bond with aluminium of LCl3 and becomes removed. So carbocation is formed here. This is C3C double bond O plus along with LCl4 minus. Now the benzene can attack very easily to this positive center, that means towards the electrophilic center, to form this positive charge will reside. Above the plane the group is C double bond O CH3, and below the plane the group is hydrogen. Then hydrogen is removed by giving up its bond pair electrons into the benzene ring, and along with LCl4 minus, and the final product is benzene. And here instead of hydrogen, here C double bond O CH3 group is there, that means acetophenone is already formed, and H plus is removed. That H plus will combine with Cl minus, which will also be removed from LCl4 minus to form HCl along with unreacted or unchanged LCl3. So here LCl3 also acts as a catalyst. So this is the mechanism of Friedel-Crafts acylation reaction. To enter an acyl group into the benzene ring, we need to take the halide of that acetyl or acyl along with anhydrous LCl3 when acetyl group is entered into the benzene ring to make a ketone, to form a ketone. So this was the Friedel-Crafts, this was some example of electrophilic substitution reaction of benzene. First we see the nitration, and after then Friedel-Crafts reaction. Okay, so in my next video we will see some other reactions, the mechanisms of some other organic reaction. Okay. Hello students, this is Bappaditya Chakravarti, and you are watching the YouTube channel Chemistry for NEET, and today we are going to discuss the electrophilic substitution reaction. Now what is electrophile? Electrophile means which are seeking of electrons. Electrons means a negative charge. So an electrophile must carry a positive charge, or an electrophile is an electron deficient species which will attack to an electrophilic center. Now what is an electrophilic center? Electrophilic center means where electron density is more, like benzene. You know the structure of benzene. Benzene is cyclic and planar structure where 6 carbon atoms form a hexagon at the same plane. Each carbon is sp2 hybridized. That means each carbon forms 3 planar bonds here, here, and here. So here hydrogen atom is present. In case of this carbon, all are trigonal, all have trigonal planar shape. This is benzene, but here each carbon has made 3 sigma bonds, so each carbon contains a pi bond, and each pi bond of one carbon is parallel to the other. Okay, so they can make a Hoydon overlapping with each other to form a pi bond. The lateral overlapping can be occur here. If your lateral bonding occurs, then these two pi orbitals can make a lateral overlapping. So here alternative pi bonds are formed, alternative double bonds are formed. The simpler form of benzene is this. Alternative double bond is present. So you know that the main 6 carbon atoms lie on the same plane, and the pi electrons are above and below the plane. So these pi orbitals, this pi bond are not so strong, so they cannot hold each other. So these pi electrons are mobile, Mobile means if some electrophilic center is there, if some positive charge is there, these pi electrons can easily be moved towards that positive center. That is how electrophilic substitution of benzene occurs. Okay, now in benzene, if we give an electrophile, say electrophile means which is carrying a positive charge, say NO2 plus. If we add NO2 plus in benzene, one of the pi bond will attack to this positive center, as these pi electrons, I've said that the pi electrons are labile. Labile means mobile, so it can move towards the positive center. If the bonds breaks from this carbon, so this carbon here, a carbocation will be formed. This carbon will contain a positive charge. So what will happen? These two bonds remain intact and the bond is broken from this carbon, so there will be a positive charge on this carbon, and here a hydrogen was already there. If the substituent NO2 comes, that electrophile comes, then one has to go above the plane and the other has to go below the plane. So the substituent electrophile NO2 plus will present above the plane and hydrogen will present below the plane. Then what happens? This bond breaks and here double bonds, making a double bond, and hydrogen eliminates. Hydrogen eliminates as H plus ion by giving up its bond pair electrons, and then double bonds again come here. This process, why this step happens, because here only 4 pi electrons are present. 2 pi bonds means 4 pi electrons are present. The compound is cyclic, and here the aromaticity regains. Aromaticity means the cyclic compound, planar cyclic compound having 4n plus 2, that means either 6 or 10 number of electrons. Here you can see that 3 pi bonds are there, so 3 to the 6 pi electrons are present. The compound is cyclic and also planar because each carbon is sp2 hybridized. That's why benzene is aromatic, and aromatic compounds are more stable than non-aromatic compounds. So to regain the aromaticity, H plus has to be removed. Okay, so this is how here hydrogen atom was present, and now in place of hydrogen there is NO2. So NO2 has replaced hydrogen. NO2 plus has replaced H plus. That is why the reaction is called electrophilic substitution reaction, where an electrophile substitutes one of hydrogen or benzene. So this is an example. This is actually nitration reaction. So this is an example of electrophilic substitution reaction of benzene. Now how this ion formed, this NO2 plus ion, is called a nitronium ion. Nitronium ion is formed when you add a mixture of concentrated sulfuric acid, and nitric acid at a temperature 50 to 60 degrees centigrade. This is nitration reaction. Nitrobenzene is formed, benzene, and here NO2. So nitrobenzene is formed. Okay, the mechanism for substitution is here, but how the nitronium ion, NO2 plus ion, is formed? HNO3, we can write HNO3 as HO bond NO2, right? HNO3. You can write HNO3 as OHO bond NO2 if sulfuric acid is given. Sulfuric acid being a strong acid, it can donate H plus ion, or it can get ionized to form H plus ions. So here H plus ion comes from H2SO4. Now that H plus ion, by this H plus ion, the oxygen of this OH group get protonated. Oxygen has a lone pair electron, so and H plus as a vacant one is orbital, so oxygen can make a coordinate bond with H plus ion. So here oxygen attacks H plus ion by its lone pair electron and a coordinate bond is formed between this oxygen and this H plus, making H2O, then bond NO2. Now since oxygen has given up its lone pair electrons, oxygen will carry a positive charge here. Now this bond breaks to form neutral H2O molecule, and since the bond pair is given away, NO2 plus ion is formed. This ion is called nitronium ion. This is the generated electrophile in the nitration reaction of benzene. Okay, so the nitration reaction of benzene is an example of electrophilic substitution reaction where the electrophile is NO2 plus, and how this electrophile is generated. If we take a mixture of concentrated nitric acid and sulfuric acid, then the oxygen of nitric acid will get protonated by the H plus ion which comes from sulfuric acid by the dissociation or ionization of sulfuric acid, and by this NO2 plus ion is formed, which is the generated electrophile. Now NO2 plus attacks the benzene ring. Here the reaction mechanism is already given here. I can write it again for you. Now this NO2 plus comes, pi bonds attacks the NO2 to form this ion. Here plus charge is formed as the bond is broken from this carbon. NO2 present above the plane and hydrogen present below the plane. Now here a new thing may occur, that is, here a resonance can occur where this pi bond shifted towards this carbon to make a double bond. So since the pi bond is broken from this carbon, the positive charge is now here, so it can be a resonating structure of this cation. Then again what can happen, this pi bond can make a double bond with this carbon, so another resonating structure is formed here. Now the positive charge will shift to this carbon, NO2, hydrogen, then hydrogen may give up its bond pair electrons to this carbon to neutralize the carbocation, to neutralize this positive charge, and as a result of that a double bond is formed, and now NO2 is present instead of hydrogen. So this is how NO2 replaces the hydrogen atom and the benzene regain its aromaticity, and so the positive charge lies between this carbon to that. So we can write this as the positive charge is dispersed over these carbon atoms, and that is why this is called the sigma complex. This is the sigma complex. So that was the nitration reaction of benzene, an electrophilic substitution reaction. Now here we will see another electrophilic substitution reaction of benzene, which is very popular, and it is Friedel-Crafts reaction.